Welcome back to the Deep Dive. Today, we are making a pretty incredible shift in perspective.
We really are.
We're moving from the scale of the telescope to the scale of the microscope. There's that great Victor Hugo quote, where the telescope ends, the microscope begins. Which of these two has the grander view?
And that's the perfect way to frame it, because for anyone who wants to understand how our world is actually built, the real action is happening beneath the surface.
So every property of a material, its strength, how it conducts electricity,
Everything. The hardness of a diamond, the reason copper is a wire and not an insulator, why glass is transparent, it is all, and I mean all, dictated by forces operating at the scale of a single atom.
Okay, let's unpack this then. The mission for this deep dive is to go straight to those building blocks of matter.
Right to the source.
We're going to be tackling the electronic structure of atoms, how the periodic table organizes them, and really the most critical part, the forces that make them stick together, the interatomic bonds.
We're using a really foundational chapter here, covering electronic structure and bonding. It's the launch pad for all of material science, really. So we're going to follow its structure pretty closely, making sure we explain every big concept, from, say, quantum numbers all the way to interaction potentials.
And this is where it gets so fascinating for me. We're going to see how a few, frankly, very strange quantum rules govern the entire universe of materials we interact with every single day.
It's a direct line from the quantum to the classical world.
So let's start where it all begins, at the very core of the atom in part one.
Let's do it.
So when we talk about the atom, we're starting with the basics, right? The nucleus with protons and neutrons, and then this cloud of electrons around it.
Exactly. But it's one thing to say that and another to really grasp the scales and the forces involved. It's not just a simple little solar system model.
Let's break down the players. First, the electron, E-. It carries that fundamental negative charge. J.J. Thomson discovered it back in 1897.
Right, though the name electron was actually coined a few years earlier by J. Stoney. But Thomson's discovery was the proof.
Then you have its counterpart in the nucleus, the proton, positively charged.
Discovered, or at least named, by Rutherford in 1919. And here's the first mind-blowing fact. The proton is about 1,836 times heavier than the electron.
Wow. So almost all the mass of an atom is packed into that tiny, tiny little nucleus.
All of it, practically. Which brings us to the third player, the neutron.
The neutral one, discovered much later, I think.
Much later. Sir James Chadwick in 1932. It's about the same mass as a proton, but, having all those protons crammed together in the nucleus brings up a huge paradox.
Right. If you just think about basic physics, all those positive charges should repel each other with incredible force. The nucleus should just fly apart instantly.
It absolutely should. The electrostatic repulsion, the Coulomb force, is enormous at that scale. So the obvious question is, what's holding it all together?
And that would be the strong interaction force.
The strong force. It's the most powerful force in the universe, but it only works over incredibly short distances, basically, within the nucleus itself. But it's powerful enough to completely overwhelm that electromagnetic repulsion and keep the atoms stable.
It's the reason matter exists, really.
Fundamentally, yes.
Okay, so from that incredibly powerful nucleus, we have to understand the electron cloud around it. Where do we even begin to model that?
Well, physicists started with the simplest possible case. The hydrogen atom is what we call the hydrogenic model. Just one single electron orbiting a nucleus with some charge, Z.
And for hydrogen, Z is just one.
Exactly. And we basically treat that nucleus as being fixed in space, right at the origin.
Okay, so you have this electron moving around a central point. You need a coordinate system.
Yeah.
And I know it's not the usual X, Y, Z we learned in school.
No, that would be very clumsy. Because the atom has spherical symmetry, it makes much more sense to use spherical coordinates. So that's r, theta, and phi.
Could you break that down for us? What are r, theta, and phi?
Think of it like a personal GPS for the electron. R is just the radial distance, how far it is from the center, from the nucleus.
Okay, it's altitude, sort of.
Sort of. And then theta and phi are the angles. They tell you its direction in space, just like latitude and longitude tell you where you are on the surface of the Earth.
And this system is useful because the main force involved, the Coulomb force.
Depends only on the distance, R. It doesn't care about the angles. The attraction between the positive nucleus and the negative electron just gets stronger as R gets smaller.
So the potential energy V var gets lower and lower as the electron gets closer.
Precisely. Now, here's where everything changed. Classical physics just completely failed to explain this.
So,
According to classical theory, an orbiting electron should be constantly radiating energy away. It should just spiral into the nucleus in a fraction of a second.
but atoms are stable, so clearly that's not what happened.
Not at all. And to explain that stability, we need a whole new rule book.
Ah.
Quantum mechanics.
And the central idea of quantum mechanics is that the electron isn't a little planet orbiting the sun. It's something else entirely.
It's a probability wave. We describe its behavior with something called the wave function, which we write as the Greek letter psi.
In this wave function, it's the solution to the famous Schrödinger equation.
It is, but the key thing to remember is that the wave function itself isn't something you can see or measure directly. It's more abstract than that.
So what does it tell us?
It tells us about probability. If you take the wave function and square it, you get the probability of finding the electron at any given point in space.
Ah, so it doesn't tell you where the electron is. It just tells you where it's most likely to be.
Exactly. And those regions of high probability are what we now call orbitals. They're not orbits, they're shapes of probability.
Okay, this is a huge conceptual leap. And when you solve that Schrödinger equation, it doesn't just give you the wave function, it imposes some constraints, doesn't it?
It does. The very mathematics of solving the equation forces the solutions to be defined by a set of integers. These are the famous quantum numbers.
The address of the electron, in a way.
That's a great way to put it. They are the fundamental code for the entire electronic structure.
So what's the first one?
The first, and maybe most important, is the principal quantum number, n inly. It can be any positive integer, 1, 2, 3, and so on.
And this defines the electron's shell, right? Like KLM.
Exactly. And for a simple hydrogen atom, N is what primarily determines the electron's energy. The energy is proportional to -1 over N squared. So a higher N means a higher energy level, and the electron is, on average, further from the nucleus.
Okay, that's N. What's next?
Next is the azimuthal quantum number, Mn. This one's a bit more subtle. It can take integer values from 0 all the way up to n-1.
And this one's about the shape of the orbital.
That's the conceptual takeaway, yes. L defines the subshell and gives the orbital its characteristic shape. So when L is 0, you get a spherical s orbital. When L is 1, you get those dumbbell-shaped p orbitals.
SPDF. That's where those letters come from.
That's exactly where they come from. They correspond to L equals 0, 1, 2, and 3.
Okay, so we have energy level and shape. What's the third number?
The third is the magnetic quantum number, Lm. This tells you how that shape is oriented in 3D space.
So which direction the dumbbell is pointing, for instance?
Precisely. M can be any integer from -L up to +L. So if L equals 1, the p orbital M can be a -1, 0, or +1.
Meaning there are 3 possible p orbitals.
Right. And they orient themselves along the x, y, and z axes. They're perpendicular to each other.
So that specific triplet of numbers n, L, and m defines one unique state, one specific orbital that an electron can occupy.
A unique state. But here's a crucial concept. You mentioned earlier that for hydrogen, the energy only really depends on N.
Right, so what does that mean for all those different states in the same shell?
It means they have the same energy. This is called degeneracy. The states are physically distinct. A 2s orbital looks very different from a 2p orbital, but in the absence of an external field, they have the exact same energy level.
So the N2 shell has 1 2s orbital and 3 2p orbitals. That's 4 degenerate states.
4 degenerate states. This idea of degeneracy being lifted or broken by the environment is going to be incredibly important when we start talking about crystals later on.
It's all starting to connect, but before we get there, how did anyone know this math wasn't just math? How did they prove it was real?
Through the light, the spectral lines. This was the first spectacular triumph for quantum theory.
So an electron normally wants to be in the lowest possible energy state.
The ground state, which is NO1.
Right.
But if you add energy to the atom, you heat it up, you shine light on it, that electron can get excited. It can jump up to a higher shell like Na2 or Na3.
But that's an unstable state. It doesn't want to stay there.
No, it wants to fall back down. And when it does, it has to get rid of that extra energy, the difference in energy between the two shells.
And it releases that energy as a photon, a little packet of light.
Exactly. And the color of that light, its wavelength, lambda, is directly mathematically tied to that energy difference. The bigger the drop, the more energetic the photon, and the bluer the light.
So the theory predicts a very specific set of possible energy drops.
And therefore a very specific set of colors or wavelengths that an atom should be able to emit. And when scientists looked at the spectrum of light from hydrogen gas, the lines they saw matched the predictions from the Schrödinger equation perfectly.
Wow.
It was an unbelievable validation. It proved that this strange, probabilistic world of quantum numbers was actually describing reality.
An amazing moment. But we're still missing one piece of the puzzle, aren't we? One more rule that lets us build up the whole periodic table.
We are the fourth quantum number, and that brings us to part 2.
Okay, so the first 3 quantum numbers, n, l, and m, they explain the energy and the shape of the orbitals perfectly for hydrogen. But they didn't quite work for everything.
No, there were still some strange experimental results, especially when atoms were put in magnetic fields. It suggested the electron had some other property, some kind of internal motion. In 1925, this was formalized as spin.
So that's our 4th quantum number, the spin quantum number.
It is. And it's deceptively simple. It can only have 2 possible values, plus 1/2, which we call spin up, or minus 1/2, which we call spin down.
And adding this one little piece to the puzzle unlocks the biggest rule of all for chemistry, right?
The biggest rule of all, the Pauli exclusion principle.
Okay, let's state it clearly. What does it say?
It says that no 2 electrons in a single quantum system, like an atom, can have the exact same set of all 4 quantum numbers.
So you can't have 2 electrons with the same n, the same l, the same m, and the same s.
Never. They can share the first 3, which means they can be in the same orbital.
But if they are, one must be spin up and the other must be spin down.
Precisely. And that has a staggering implication.
It means that any given orbital can hold a maximum of exactly 2 electrons.
2 electrons, and that's it. But the principle is more than just a capacity rule. It's an active force. If you try to push 2 electrons with the same spin into the same space, you get an enormous repulsive force.
So it's the Pauli exclusion principle that stops matter from just collapsing on itself.
It's the fundamental reason you can't push your hand through a table. It's what gives matter its volume, its rigidity. It's not just an accounting rule for the periodic table. It defines the physical world.
That is a core insight. Okay, so with this rule, we can now calculate how many electrons fit in each main shell.
We can. The total capacity for a shell n turns out to be 2 times n squared. So for n1, the K shell, you get 2 electrons.
For n2, the L shell, you get 8.
For angle 3, the M shell, you get 18, and so on.
But when we actually start building up atoms with more and more electrons, they don't just fill up shell 1, then shell 2, then shell 3 in that simple order.
No, and this is a classic point of confusion. For atoms with many electrons, the electron repulsion starts to shift the energy levels around. The subshells start to overlap in energy.
So electrons will always go to the lowest energy spot available.
Always. And because of this overlap, it turns out that the 4's subshell, which is part of the 4th shell, is actually lower in energy than the 3rd subshell, which is part of the 3rd shell.
So after you fill the 3p orbitals, you don't go to 3rd next. You jump out to 4s first.
You fill 4s, and only then do you go back and start filling the 3rd orbitals. This specific order, 1s, 2s, 2p3s, 3t4s, 3rd 4p, is the blueprint for the entire periodic table.
And it explains the properties of whole blocks of elements.
Especially the transition metals, which are defined by the filling of those orbitals.
So if the quantum numbers and the Pauli principle are the genetic code, the periodic table is the organism. It's the physical expression of those rules.
A perfect analogy. It organizes elements based on the configuration of their outermost electrons, their valence electrons.
And the structure is so elegant, the horizontal rows are the periods, and they correspond to the principal quantum number, n.
Right. Every time you start a new row, you're starting a new principal shell.
And the columns, or groups, they cluster elements with similar chemical behavior. And that behavior is all about how full that outer shell is.
You can see it most clearly at the far right of the table with the noble gases, helium, neon, argon.
Why are they so stable,
Yeah.
so unreactive?
Because their outermost shell is completely, perfectly sold. They've reached the energetic ideal. They have absolutely no motivation to gain or lose electrons, so they don't react with anything.
And then on the total opposite side of the table, you have the alkali metals, column 1.
The most reactive metals. They've just started a new shell. They have one single lonely electron in that outer orbital.
Like sodium, which is a neon core plus 1,3's electron.
And that one electron is very weakly held. The atom is desperate to get rid of it so it can have the stable, filled shell configuration of neon. That's why they're so explosively reactive.
We can even map the whole table out based on which type of orbital is being filled. This
Yeah.
gives us the blocks, right?
Exactly. The first two columns are this S block.
Yeah.
The last six columns are the P block, and that big section in the middle.
That's the D block, the transition elements.
And that connects back to the weird filling order. Because the n's orbital fills before the n1d orbital, many of the transition metals have the same outer shell, usually n squared, while that inner d shell is being filled up.
Which explains why so many of them have similar chemical properties. Their outermost layer, the part that interacts with the world, looks the same.
It does. Then, tucked away at the bottom, you have the F block, the lanthanides and actinides.
The 2 rows of 14 elements.
Right. And here, the 4 and phi orbitals are being filled. But the crucial thing about orbitals is that they are buried deep inside the atom's electron cloud. They're shielded.
So even as you add electrons to those f orbitals, the outside of the atom looks almost identical all the way across the series.
Which is why the lanthanides, for example, are notoriously difficult to separate from each other. Chemically, they're nearly identical twins.
And there's a kind of dividing line on the table, isn't there? A diagonal that separates the metals from the non-metals.
There is. It's called the Zintl line. Everything to the left and bottom tends to be metallic. They want to lose electrons. Everything to the right and top tends to be non-metallic. They want to gain electrons.
Okay, so we've established the internal rules. Now let's talk about how those rules translate into observable, predictable trends across the table. The atom's readiness to interact.
Absolutely. This is where the quantum rules become practical chemistry.
Let's start with something really basic. The size of the atom. We know it's mostly empty space, but that electron cloud gives it a certain diameter.
Roughly 10 to the minus 10 meters, or 1 angstrom. But that size isn't constant. It changes in the very predictable ways, driven by a tug of war between two different effects.
Okay, the first trend is as you go across a period from left to right, the atomic radius actually gets smaller.
It decreases, which, as you said before, is completely counterintuitive. You're adding more protons, more neutrons, more electrons. The atom is getting heavier, but it's shrinking.
So why does it shrink?
Because while you're adding an electron, you're adding it to the same principal shell. But at the same time, you're adding a proton to the nucleus. That extra positive charge pulls much more strongly on the entire electron shell, sucking the whole cloud inward. The pull wins.
Okay, that makes sense. But the trend is the opposite as you go down a group.
As you go down a column, the atomic radius increases significantly.
And that one's more straightforward, I guess.
It is. Each step down the table means you're adding a whole new principal shell. The N value is increasing. The outermost electrons are just physically much, much further from the nucleus.
Man, why does the exact size of an atom matter so much in material science?
Because crystals are all about packing. Atoms have to fit together in a precise, repeating lattice. If you try to substitute an atom in a crystal with another one that's too big or too small, it creates a strain. The whole lattice has to distort to accommodate it.
And that distortion costs energy and affects all the properties.
Every single one. Mechanical strength, electrical conductivity, everything. Size is a critical design parameter.
Okay, beyond size, there's an even more important chemical trend. Electronegativity?
This is the big one. It's a measure of an atom's fundamental tendency to attract electrons to itself when it forms a chemical bond. It's chemical hunger, if you will.
And there are a few ways to measure this, but the Mulliken scale is really insightful.
It is, because it's not just an arbitrary scale. It defines electronegativity, which we call X, as the average of two other real measurable energies. It's 1/2 of the ionization potential plus the electron affinity.
Let's define those terms. What is ionization potential?
That's the energy you have to put in to rip an electron away from a neutral atom, creating a positive ion.
So elements on the left side of the table, the metals, they have a low ionization potential. They give up that electron easily.
Very easily. And as you go across the period to the right, ion increases a lot because those outer electrons are held much more tightly by the nucleus.
Okay, and the other term is electron affinity, A.
This is sort of the opposite. It's the energy that is released when a neutral atom gains an electron to become a negative ion.
So the halogens on the right side must have a very high electron affinity. They really want that extra electron.
They do. Adding that electron releases a lot of energy and gets them to a very stable state. So a high electronegativity, a high value for X, means the atom has both a high ionization potential and a high electron affinity. It holds its own electrons tightly and strongly desires more.
And this gives us a much more rigorous definition for metals and nonmetals.
Exactly. Metals have low X. They are electropositive. They want to lose electrons and form cations. Nonmetals have high X. They are electronegative. They want to gain electrons and form anions.
And this fundamental drive leads directly to the concept of valence.
Or oxidation number, yes. It's just a count of how many bonds an element tends to form.
And it's all driven by one thing.
The relentless drive to achieve that stable, filled shell configuration of a noble gas. That's the only rule that matters.
So let's run through a few examples. Sodium, Na, as one valence electron.
So it desperately wants to lose that one electron to get the configuration of neon. Its valence is +1.
Chlorine, Cl. It has 7 valence electrons.
So it desperately wants to gain one more to get the configuration of argon. Its valence is -1.
And magnesium, Mda, with 2 valence electrons.
It will lose both of them to get that stable neon core. Its valence is +2. It's a simple counting game based on the quantum rules, and it governs all of chemistry.
So we have the atoms and their tendencies. Now we finally get to what happens when they meet, the formation of bonds.
And this is the realm of quantum chemistry. Using the Schrödinger equation to figure out how atoms interact, what the energies are, and why molecules and solids are stable.
Now, solving that equation for anything more complicated than hydrogen is, well, incredibly difficult.
It's computationally massive. So over the years, a number of very powerful models have been developed. There were early ones, like valence bond theory, which looked at pairing electrons between atoms.
And more modern ones. More modern approaches include molecular orbital theory, where the orbitals belong to the whole molecule, and especially density functional theory, or DFT, which is a powerful computational method for calculating the ground state energy of complex materials by looking at their electron density.
But all these models are trying to do the same fundamental thing, right?
They're all trying to map out the energy landscape as two atoms approach each other.
And no matter what kind of bond we're talking about, there's one absolute rule for it to form.
The total energy of the bonded system must be lower than the energy of the two separate atoms. That difference in energy is what we call the binding energy. It's the payoff for forming the bond.
And the best way to visualize this is with the potential energy curve, V of R.
It is arguably the most important graph in all of material science. It plots the potential energy, V, against the distance between the two atoms, R.
Okay, let's walk through it. We start with two atoms very far apart. As they get closer, what happens to the energy? At large distances, the energy starts to decrease. This is the region where attractive forces are dominating. The atoms are drawn to each other, seeking a lower energy state.
And that attraction continues until the energy hits a minimum point, a well in the curve.
Right. That lowest point is Vmin, and its depth is the binding energy. The distance where it occurs, RAMM, is the equilibrium bond length. That's the most stable separation for the two atoms.
But what if you try to push them even closer than that?
Then the curve shoots up almost vertically. This represents a massive repulsive force that kicks in at very short distances.
And this repulsion is?
It is, once again, the Pauli exclusion principle in action. You're trying to force the electron shells to overlap to put electrons into the same quantum states, and the universe just says no.
So the stable bond length, RAM, is that perfect sweet spot where the long-range attraction is exactly balanced by the short-range Pauli repulsion.
Exactly. It's the point where the net force on the atoms is 0. And in a real crystal, every single atom sits in a position like this, where the sum of all the forces from all its neighbors cancels out perfectly.
Now, this simple curve is great for two atoms, but in a real solid, it's more complicated.
Oh, much more. You have many body interactions, directional forces. You need very sophisticated models to capture all that. But this simple potential curve gives us the fundamental concept for all types of bonding.
Okay, so let's use this concept to break down the 4 primary bond types. First up, the ionic bond.
The ionic bond is all about a huge difference in electronegativity. You typically see it between an alkali metal from the far left of the table and a halogen from the far right, like sodium and chlorine and table salt.
And the mechanism here isn't sharing, it's a complete transfer.
A complete handover. The sodium atom gives its one valence electron entirely to the chlorine atom.
So the sodium becomes a positive ion, a cation, and the chlorine becomes a negative ion, an anion. And both now have that stable, filled, noble gas shell.
Right. And this transfer also changes their size, remember? The sodium cation is much smaller than the neutral atom, while the chloride anion swells up because of the extra electron.
And what holds them together now is just the attraction between that positive charge and that negative charge.
A pure electrostatic attraction, the Coulomb force. And because that force is non-directional, it just pulls in all directions, Ionic crystals tend to pack as densely as possible to maximize the number of positive-negative neighbor pairs.
So the total energy of the bond is the sum of that long-range Coulomb attraction and that very sharp short-range Pauli repulsion.
That's the whole picture, and a mathematical model like the Lennard-Jones potential is designed to capture exactly that interplay between a gentle long-range attraction and a fierce short-range repulsion to predict the bond energy and length.
Okay, so that's ionic transfer. What about the covalent bond?
Covalent bonds happen when the atoms have similar electronegativity, so neither one can just rip an electron from the other. Instead, they have to share.
And this sharing is a purely quantum mechanical effect.
It is. Take the simplest case, the hydrogen molecule, H2. For the two electrons to occupy the space between the two nuclei, the Pauli principle demands they must have opposite spins. One spin up, one spin down.
And when they pair up like that, it creates a region of high electron density between the atoms that holds the two positive nuclei together.
Right. It creates a low-energy bonding state. If their spins were parallel, they would actually repel each other, creating a high-energy anti-bonding state.
Now, unlike the ionic bond, the covalent bond is very picky about direction, isn't it?
Extremely directional, because it relies on the direct overlap of specific atomic orbitals. This dictates the exact angles and geometry of molecules and solids.
And this leads to concepts like hybridization, which is so important for carbon.
It's everything for carbon. Carbon can mix its 1s orbital and 3p orbitals to create 4 identical hybrid sp3 orbitals.
And what's the shape of those?
They arrange themselves in a perfect tetrahedron with bond angles of exactly 109.5 degrees. This rigid three-dimensional network is what makes diamond the hardest material we know. The bonds are strong, and their geometry is locked in place.
Okay, so from sharing to our third type, the metallic bond.
The metallic bond is found in electropositive elements, metals, that don't hold on to their outer electrons very tightly.
So what happens to those electrons?
They basically detach from their parent atoms entirely. They become delocalized and form a kind of mobile sea of electrons that flows freely throughout the entire solid.
So you're left with a fixed lattice of positive ion cores sitting in this fluid of negative charge.
That's the picture. And this electron sea is the defining characteristic of a metal.
Because that mobility is what allows for high electrical and thermal conductivity.
Exactly. The electrons are free to move and carry charge or heat energy. It's also why metals are opaque. That sea of free electrons is incredibly good at absorbing and re-emitting photons of light.
And what does this mean for the crystal structure?
Since the bonding isn't really directional, it's just the attraction between the positive cores and the uniform negative sea, the atoms tend to pack together as efficiently as possible, like stacking marbles. This leads to very dense, close-packed structures.
So we have transfer, sharing, and delocalization. What's the last weakest bond?
The van der Waals bond. This is the bond that holds neutral atoms or molecules together.
So there's no permanent charge, no sharing. Where does the attraction come from?
It comes from tiny, instantaneous fluctuations in the electron cloud. At any given moment, the electrons in a neutral atom might, just by chance, be distributed a little unevenly.
Creating a temporary tiny little dipole, a slight positive side and a slight negative side.
Exactly. And that temporary dipole can then induce a similar dipole in a neighboring atom, leading to a very weak, very fleeting attraction between them.
It sounds incredibly subtle.
It is. And because it's so temporary, the force is extremely weak and it falls off incredibly quickly with distance. It's proportional to 1/i to the 6th power. It's negligible unless the atoms are almost touching.
So where do we see this bond in action?
It's what allows noble gases like argon to solidify at very low temperatures. And it's the force between molecules in many solids. A great example is graphite.
Ah, right. The carbon atoms within the sheets are held by strong covalent bonds.
Immensely strong. But the sheets themselves are only held to each other by these weak van der Waals forces. That's why they can slide past each other so easily, making graphite a great lubricant.
Okay, so we have these 4 pure bond types. But in the real world, it's not that clean-cut, is it?
Almost never. Most real bonds are a hybrid, a mix of different characters. The most common is a mix between ionic and covalent.
So it's not a complete transfer or perfect sharing, but something in between.
Right. You can think of it as a spectrum. And you can actually estimate the percentage of ionic character in a bond based on the electronegativity difference between the two atoms.
A concept developed by Linus Pauling.
Exactly. The bigger the difference in electronegativity, the more ionic the bond is, because the shared electrons are pulled more strongly toward one atom. If the difference is small, the sharing is more equal, and the bond is more covalent.
And this mix has real consequences for material properties.
Absolutely. If you compare two semiconductors like zinc selenide and gallium arsenide, the bond in ZnS is significantly more ionic. And that difference affects their crystal structure, their electronic properties, their optical properties, everything.
It's not just the bond itself, though. The local environment inside the crystal also plays a huge role.
A critical role,
Right.
especially for the optical and magnetic properties. This is where the symmetry of the crystal field comes in.
So this is most important for transition metals with those d and f orbitals.
Right. Remember how we said that in a free atom, all 5 d orbitals are degenerate? They all have the same energy?
Yes.
Well, as soon as you put that atom inside a crystal, it's surrounded by the electric fields of its neighbors, and that field breaks the degeneracy.
How does it do that?
Imagine, our transition metal ion is at the center of an octahedron, surrounded by 6 negative ions. Some of the d orbitals have lobes that point directly at those negative neighbors.
So they would feel a strong electrostatic repulsion.
A very strong repulsion, which pushes their energy level up. Other d orbitals have lobes that point between the neighbors. They feel less repulsion, so their energy level is lowered.
So local symmetry has split the 5 d orbitals into 2 or more distinct energy groups.
Exactly. It's called crystal field splitting. And this splitting of energy levels is what allows materials to absorb specific colors of light, giving them their characteristic color, or to exhibit unique magnetic behaviors. The geometry of the crystal literally tunes the electronic states.
That's a powerful connection. So let's bring it all together. Let's do a quick overview of how each bond type leads to the macroscopic properties we see every day.
Sounds good. Let's start with ionic solids, like salt. They have strong non-directional bonds. This makes them hard, brittle, with very high melting points.
And because the electrons are stuck to their ions, they're electrical insulators.
Great insulators, and they're often transparent because you need a lot of energy to excite those tightly bound electrons.
Okay, covalent solids, diamond, silicon.
The strongest, hardest materials we have with the highest melting points. Again, they're great insulators because the electrons are locked into those directional bonds, but they are also very brittle.
Then we have metals.
Non-directional bonding, which leads to dense packing. But the key is that electron C. It makes them fantastic thermal and electrical conductors.
And it also allows them to be ductile, to be bent and deformed without breaking.
Right. The planes of atoms can glide past each other within that electron C, and of course they're opaque.
And finally, the van der Waals materials.
Held by the weakest force, so they are very soft, have very low melting points, and expand a lot when heated. They're insulators because the electrons belong to individual neutral molecules.
It's amazing how directly the microscopic bond dictates the macroscopic world. And this understanding didn't just appear overnight.
Oh, not at all. It's the culmination of centuries of work, really accelerating in the late 19th and early 20th centuries.
You have to start with Mendeleev and the periodic table in 1869. He organized the elements so perfectly that he could predict the properties of elements that hadn't even been discovered yet.
He famously predicted silicon, which we now know as germanium. It was an incredible feat of scientific intuition.
Then came the physical discoveries that challenged that framework. Thomson's electron, Rutherford's nucleus. And then the quantum revolution just blew the doors off everything.
It started with Max Planck in 1900. His idea that energy isn't continuous, that it comes in discrete packets called quanta. That was the break from classical physics.
Niels Bohr then applied that idea to the atom with his planetary model and quantized energy levels.
And then things got even stranger. Louis de Broglie in 1923 suggested that particles like electrons also behave like waves, wave-particle duality.
Which led to Werner Heisenberg's uncertainty principle in 1927. The idea that there's a fundamental limit to what we can know. You can't know both the exact position and momentum of a particle at the same time.
And the person who put it all together into a coherent mathematical framework was Erwin Schrödinger in 1926. His wave equation and the wave function, psi, gave us the engine to actually calculate the probability distributions for electrons. It's the foundation for everything we've talked about today.
So to recap this deep dive, we started with just 4 simple quantum numbers that define an electron state.
And we saw how those numbers, combined with the absolute rule of the Pauli exclusion principle, force the periodic table to have the structure that it does. It dictates the shells, the blocks, and the chemical personality of every element.
And from that, we saw how the 4 fundamental bond types, ionic, covalent, metallic, and van der Waals, are the direct result of how those electrons interact to achieve stability.
And those bonds, in turn, determine every single macroscopic property of a material. It's the ultimate link between the microscopic rules and the engineering world.
And that's really the key takeaway, isn't it? Understanding bonding is not just abstract theory. It's the reason copper conducts and diamond is hard.
It's why materials behave the way they do. It's the most fundamental level of engineering.
So let me leave you with a final thought to mull over. We're now at a point where material scientists aren't just discovering materials, they're designing them. They do this by intentionally creating materials with mixed bonds or by using weak secondary bonds to get very specific properties.
Combining the strength of a covalent material with the ductility of a metal, for instance.
So consider this. If you could turn a dial and precisely adjust the percentage of ionic versus covalent character in a bond, what completely new material, what new combination of properties could you design? What problems could you solve?
That's the future of material science. It's an exciting place to be. We hope you enjoyed this deep dive into the very fabric of matter.
Thank you for joining us, and we'll see you next time.